let's do an example. So here's the machinery we developed to deal with time-independent perturbation theory. And so let's try this on a pretty simple example, and we'll only use the energies. And so it actually turns out that the majority of the time, I would say, people are only interested in the energies. So we have the wave function there, but typically the energies will be the thing people are most interested in. So let's look at a general two-level example. Okay, so here's the two-level example. So again, our Hamiltonian looks kind of like this, where this is our unperturbed Hamiltonian that has an exact solution. And so what does that mean? Well, that means that there's two wave functions, right? So we'll call them psi 1 of 0 and psi 2 of 0. And of course, in this case, in this particular system we're looking at, they would represent it this way here, but that's not necessarily super important right now. But this one has an energy, exact energy of E1, 0, and this is E2, 0. So just pause for a second and make sure that this nomenclature makes sense, because I think that's one of the hardest parts of doing this stuff. So that's the exact, and then here we have a perturbation potential, and we're not saying what it is, but we were saying that we've already taken that and basically expressed it out in a nice matrix form. Remember, each one of these pieces has this form here, where again these guys are just these over here. Okay, and so now when you're actually doing this, it'll work out that sometimes this matrix element is not easy. In fact, that'll be sometimes the hardest part of your problem, is figuring that out. So here we're just completely skipping that just to kind of get used to how this system works. And so we've assumed that we've done that, and we have this nice perturbation potential H prime. And so once we have that, how do we find our approximate energies? And so let's go through here and do this here. So here's our picture. And so what we do is we just basically take these. Now, again, these deltas, this is another really confusing part. The deltas are just there so we can kind of see what order each term is. And so eventually we're going to just call delta equals, and I keep calling that delta, but it's a lambda equal to 1. Okay, and so we're just going to get rid of those, but I'm keeping them here just so you can kind of see. But so in this problem, if this was given to us, so we got this new perturbation potential here, and here's the equations that we use to figure out what our energy corrections are. So what we're doing here is, so that the new energy E1, it starts as the old one. So this whole idea of perturbation theory is we already figured out this energy for one system, and now we're just going to perturb it a little bit and find the corrections to this. So the first correction is this guy, which is just going to be this piece right here. Okay, so if that is confusing, just pause and think about it. But this matrix element, right, for the E1n, right, it would just be putting a 1 in for n and a 1 here and a 1 there. And so that would be our first order correction. And again, for a lot of what we do, this will be essentially what we're trying to find, is that first order correction. Now the second order correction is a little bit more ugly. And so let's write this out here. No offense. So again, it's a sum of m not equals to m. And what I can do here is say that, okay, so what I'm trying to find in this case is I'm trying to find the second order correction to the first energy. Okay, this is my first energy, second order correction. So I can set everything in here n equals to 1, just to kind of clean that up a little bit. It's still going to be kind of ugly. So we got psi m 0, and let me like that, and then this is the matrix element of H prime, and then here we can just set that one to be the 1. So that's the psi 1 of 0, and then down here this is E1 of 0, so this guy over here minus some general EM of 0. And so now what happens is you would go through and you'd sum over the different matrix elements. And if you look here, okay, so we're saying that m is not equal to n. So these matrix elements are going to be these guys over here, these off diagonal ones. So we just use the H prime 1, 1 over here. Well, these ones are going to be off diagonal because we've sort of defined that this can't be 1 and 1 at the same time. And so those are the pieces that we'll sort of be looking at for that. And in theory, right, this sum could include an infinite number of things, depending on what system. Now, this is a nice two-level system. And so if you look here, it only has one sum, right? We're saying that m can't be equal to n. And so the only other state we have would be the 2 state. And so this is basically the simplest case we could possibly have. And what I'm just going to do here is just write this out. So generally, again, you'll be summing over a bunch of these terms, but here there's just one. So that's why it's kind of a nice example to start out with. So we got this one here, plus this, and then here, so this thing I would write as h prime 1, 2, absolute square of that, and then all over E10 minus E20. And again, plus dot, dot, dot. So that's the first correction, and then of course we can go in and find the corrections to the second order energy. So now this guy will be this matrix element, the one we haven't used, right? So the diagonal ones are generally going to be the first order, and then the sum here, now technically it should be H21 prime absolute squared. Of course, we know that in a Hermitian matrix, this will be the same either way. And then over this would be E20 minus E10. So again, so this is the machinery, and what you need to do to actually write this out is you need to do these matrix elements and then know these energies. But everything we have should be basically written out here. So now what we're going to do is we're going to go through, and this problem you can actually do exactly, or at least pretty close to it, and then show that what you get is the same as you do here with our approximation technique. So it's kind of a nice exercise to do. So I'm going to go do that now, but I would say stop here if you're not sort of certain how we got all these terms, and just make sure that all this makes sense to you. This is sort of the new stuff we're going to be doing. Okay, so now let's go through and try to find these energies exactly. So the way we do that is, again, the way we're setting up our Hamiltonian is it's this original Hamiltonian that we have already solved plus the perturbation. So I'm just going to throw it all together, and we can go through and try to find the eigenvalues for this matrix. All right, and so just to make that a little easier, we're going to just make it, we're going to call it H is equal to this piece here. So like A would equal, this piece here. B would equal this piece over here, and then we're going to make a little simplification in that these two guys are, complex conjugates of each other, and so we can write it as C and C star, just to make things a little bit easier. So we're going to, for the time being, just write our matrix out that way. And so to go through and find the eigenvalues, we would do the determinant of our matrix minus, what we call that piece that gives us those eigenvalues. So we do the determinant. I get A minus E, B minus E minus absolute square of C equals 0. And so I'm going to write this out such that you can solve this using a quadratic formula. And so here's my result. And so here, just to kind of, what we did is, so our quadratic formula looks something like this in general. B squared minus 4AC over 2A. So here, A would be our coefficient here. So I know this is super confusing, so I got two different kinds of A's and stuff. But A in our quadratic formula would be the factor here, which is 1. This would be our sort of B term in the quadratic formula. And this would be our C term. And so since this is just 1, I'm going to write it out just be a little bit fancy. So negative B divided by 2 plus or minus, and I'll bring that 1/2 into here. So it's B squared over 4, and then this 4 over here cancels. And so that's how I wrote it out over in here. So this is 1/4. Again, that comes from that 2 in the downstairs part, and then this is the sort of next part. So again, I would definitely advise to go through this and make sure you follow this. But then we come out with this as being our sort of, this would be our exact answer. So if we plugged in everything from before for that A and that B over here, right? Right here, we could go through and find the exact energies. Now, we don't care about the exact energies. What we're going to do is find an approximate value. And so here, I just sort of cleaned up this inside a little bit, made it look like this here, and we're going to take the Taylor series of these guys here. Okay, we're assuming that the C term is going to be pretty small. Now, why can we do that? Well, if we go back to our definitions over here, right, the A term has the original energy. The B term has the original energy. These terms are bigger than the H prime terms. And so since the C is dependent on the H prime terms, we can assume that that's much smaller. So again, I go through here after I write this out. And so this is sort of our exact picture. And we're going to make our approximation here. So this is literally, I do 1 plus 1/2 times the second term. Now there'll be other terms, but again, we're only caring about the first couple of terms. So make sure, you stop and go through this. But at the end of the day, what I come out with here is I got this picture. And so you can kind of write this out this way here. So this energy would equal, I could write as A divided by 2 plus B divided by 2, and then plus or minus 2 terms from here. So I've got this times 1, so A over 2 minus B over 2, and then the second term is 1/2 A minus B times this guy. And so the 2 cancels there, so the half cancels with that 2, and A minus B cancels with one of the factors down there, and we're left with plus absolute square of C over A minus B. And again, there's next terms, but we don't necessarily care about those. And so when you unpack this, you get the two sort of approximate values for E1 and E2 look like this. And so now we're going to go back to that original definition and plug those guys in. And when we do this, what happens is we of course get something very similar to what we had already found using our perturbation theories. So for the E1, when I plug that in, I get this is that first piece, right? Again, the lambdas are just there to kind of hold the place a little bit, and so they're important right now. So for instance, this lambda, right, that tells me that this is a first order correction, and so it's definitely smaller than this guy. Now over here, this guy, there's 2 orders of lambda, which tells me that's a second order correction, so there's 2 of those H prime pieces, and so it's going to be even smaller than this one. So this is definitely the second order term. And inside here, since we're adding these really big terms with the little terms, I can just cross these guys out. Just say, well, they're probably pretty small. They're not going to make much of a difference. And so when I do that, and then I just set that lambda equals to 1, and guess it's just a placeholder, I get this here, which if you go back a few slides, this is exactly what we wrote down from perturbation theory. So hopefully that's cool. That what we can do is, by going through and actually finding the exact answer, we get the same terms that we got for the perturbation theory. So this works out, in the case like this where it's a 2-level system, it's kind of, you could argue which way was easier to calculate this, but for bigger systems it's going to be much easier to use perturbation theory, and so that's why we're doing it. So again, here's our equation, and that is what we came out to be. I want to hit home again that, these matrix elements here are going to be the meat of what we're doing. So we don't want to sort of be like, hey, these are easy, but we're just trying to sort of set up the picture. And then, of course, finally, we can write out these terms here for the second order one, which again will work out to be what we wrote down originally. The one kind of piece that's a little subtle is that we typically write this in terms of the energy that we're talking about minus the other energies. And so there's this negative sign here, but that negative sign gets fixed up because when you plug in the values for A and B, you're going to end up with these reversed. And so that's basically all that we did there. But again, hopefully that is helpful, and we'll talk much more about this in class. Thanks.